Hello everyone, my name is Koma Signolo. Welcome to another video by Attention Matrix, where we try to make learning fun and easy. Please comment, like, and subscribe if you would like us to continue making this content and you enjoy it or find it helpful. Now on to the next video. Let's get right into it. Okay, welcome back to another video on momentum. In this video, we will be looking at momentum in 2 dimensions. So far, we've looked at momentum in 1 dimension, where we had objects moving only in 1 direction, and we calculated the momentum in that direction. Okay, so for momentum in 2 dimensions, we are dealing with 2 directions. So by 2 dimensions will simply mean 2 directions. Okay, 2 directions. We are looking at momentum in not only just 1 direction, but in 2 directions. And by those two directions, we mean the x direction and the y direction. Okay, so that's basically the difference between momentum in 1 dimension and momentum in 2 dimensions. 2 dimensions simply means that we've got momentum in 2 directions. Okay, and we've got to calculate that momentum in 2 directions. Now, let's explain that a bit more. Let's say you've got remember, for momentum in 1 dimension, if you've got a car for momentum in 1 dimension, right? If you've got a car for momentum in 1 dimension and a car there, right? And these cars are moving towards one another. These cars are moving towards one another, and this is a closed system, meaning that there is no external force acting on either one of these cars, right? Remember that when these two cars collide, right? When they collide, they will continue moving either that way, or they will stop. Okay, but what I'm showing you here is that this here is 1 dimension, because we are only considering the horizontal direction, the x direction. Okay, so we're considering the x direction, and that is therefore 1 dimension. Okay, so now let's look at a situation where we would have 2 dimensions. Let's say you have a car. Let's say you've got a car traveling this way, right? Car is traveling in this direction. There's a road there. This car is traveling on this road in that direction, and the road continues on there. And you've got, say, another road there, and you've got another car traveling from that direction. Okay, you've got another car traveling from this direction. Okay, now this car is moving that way, this car is moving that way, right? And let's say the road does that and the road does that, whatever. Okay, now you will agree with me that these two cars are traveling in different directions in terms of whether it's the x direction or the y direction, right? This car down here is traveling in the x direction, and this car is traveling in the y direction. Okay, now when these two cars collide, they will collide at that point there. When these two cars collide, say they continue moving in that direction. Okay, so they don't move in just the x direction, or they don't move in just the y direction. They move in the combination of both directions at some angle there. Okay, so this is an example of momentum in 2 dimensions. Now, how would you handle this situation? Well, remember the law of conservation of momentum. The law of conservation of momentum states that the linear momentum in a closed system remains conserved, or remains constant, right? So let me just write it out again as a reminder. The law of conservation of momentum states that the linear momentum in a closed system is constant, right? It's conserved. It does not change. It stays the same. You could say that in any any number of ways and it'd still be correct. Okay, so that's what we have. We have the law of conservation of momentum, and it says that the linear momentum in a closed system is constant. Now, that law still applies here. That law still applies in two-dimensional in our two-dimensional analysis of momentum. How does that law apply? Because we see that here we've got momentum in this direction, and here we've got momentum in that direction. And to further complicate things, what we have afterwards is none of those two directions. We have a completely different direction that is neither x or y, but we still want to calculate the momentum of the cars after. Now, how do we do that? How do we tackle this situation? How do we deal with this situation? Well, it's easy. In order for you to do your analysis of momentum, you split. Okay, you split your velocities. You split your velocities into x and y components, and then you solve. Okay, I will show you, I will demonstrate just now. You split your velocities into x and y components, and then you solve. Okay, so remember that your velocity is a vector. It can be split into components, and if it can be split into components, it means that you can look at your velocities in different directions. You can look at your velocities in the x direction, you can look at it in the y direction, and you can look at it at different angles as well. Okay, so let's go back to the car example up there. So what you have here is the car traveling in the x direction. You've got a car traveling in the y direction. The two cars collide and move in that direction there at an angle. Okay, so now in order for you to be able to use the law of conservation of momentum, you're going to have to look at the momentum of this car in the x direction. Because it's traveling in the x direction, you're going to have to look at the momentum of that car in the y direction because it's traveling in the y direction. Now, for when the cars collide and move at an angle together, you're going to split the velocity. So if you look at this thing, the velocity is traveling in this direction, right, at an angle. But you're going to have to take this velocity because it's moving in this direction. You're going to have to take that velocity and you're going to have to split it in the x direction and in the y direction. You're going to have to find the x component of that velocity and the y component of that velocity, meaning that you will have to split that velocity into its components, into that direction and into that direction. Why? Because this direction corresponds to the direction of that car there, and this direction corresponds to the direction of this car there. So it means that this velocity x, the component of this velocity, it means that you can use it in your equation of momentum with the velocity of the car initially before it went into the collision, right? And this velocity here, velocity y, you can use with the velocity, the initial velocity of the car before the collision. So now you've essentially split your situation into two. What did you do? You split it into two. How did you split it into two? Let's show you how you split it into two so that you can analyze your momentum for the two scenarios. Remember, you had a car, right? There's your car there. You've got your car, and your car collided with the car from that direction, and then it moved in that direction, right? But here, you're not interested in this direction. You just want the x component and you want the y component. So if you have the x component, then you don't need this because you've got the x component, right? So now you've got this car still moving in that direction at that velocity vx, the component of the velocity that you would have found. So now you're analyzing momentum in just one direction. Okay, so the same thing for the car on top. So the car on top was moving in this direction. Okay, it's moving in this direction. It's moving in this direction, and it collided with the car that was coming from that direction, right? And then they moved at an angle down there. But you're not interested in this direction, this angled direction. You want that component, right? You want that component of the velocity that we call Vy. So then you don't want this. You only use the resultant velocity to find the components. Once you find the components, then you can analyze this on its own. Okay, now you can treat these two scenarios as separate closed systems. Okay, so you can analyze this one on its own, and you can analyze this one on its own. Okay, and then you can find the relevant velocities that you would have been asked to find. Okay, let's give you another example. Let's give you another example to make this make sense. Say you have a pool table, right? You've got a pool table and you've got a ball. Here's your ball here. Or let's make it a bit more complicated. Say you've got a ball here, and this ball is moving in this direction, right? This ball is moving in this direction, and you've got a ball here standing still. Now, when I'm going to call this ball 1 and I'm going to call this ball 2 to differentiate between the balls. Now, this ball is moving in that angled direction V, so it's moving at an angle, right? Here's your x's directions. This is your x direction, this is your y direction, but this car is moving at an angle like that, right? This ball is moving at an angle like that, so it's moving at an angle like that. This one has a velocity of 0. It has a velocity of 0, so it's not moving at all. Now this ball strikes that ball. Ball number 1 strikes ball number 2. Once ball number 1 strikes ball number 2, ball number 2 moves in that direction. Okay, so I'm going to draw it down here. Ball number 2 moves in that direction. And ball number 1, say, changes direction slightly. It moves, or let's say it moves vertically now. Okay, it moves down. It moves down like that. There's ball number 1 and there's ball number 2. So initially, okay, so this one has a V final, and this one has also a V final. Now, what you have here is that you've got this ball, right? It's moving at an angle. It's moving at an angle. It strikes ball number 2 such that ball number 2 moves to the right like that at a certain velocity, and ball number 1 continues moving downwards at a certain velocity. You see that here we're dealing with different directions. We're dealing with an angle, we're dealing with the x direction, we're dealing with the y direction. What happens here is that in order for you to calculate the velocities, the different velocities, depending on the information that you're given, remember that these balls have masses, right? Ball number 1 has mass number 1, ball number 2 has mass number 2. The masses of the balls don't change. Okay, the masses of the balls don't change, so just keep that in mind. But what happens is that the direction of the balls change. Now, since the direction of the balls change, in order for you to calculate the velocities of this ball, the law of conservation of momentum applies still. But what happens is that you've got to break down anything that is at an angle. You're going to have to break down into x and y components. Any velocity, any of the velocities that is at an angle, you're going to have to break down. To its x and y components. So this here, that angle there, you're going to have to break down into that and that. This is going to be Vx initial of ball number 1. This is going to be Vy initial of ball number 1. Then this one will have Vy final of ball number 1, because it's moving vertically downwards, but it does not have a Vx final because it's not moving in the x direction. You see that? And then for ball number 2 just has Vx final of ball number 2, and Vx initial of ball number 2 is that value there of 0 because it wasn't moving at all in that x direction. Okay, and then you use your law of conservation of momentum. Now, how would you do that? You use your law of conservation of momentum by considering one direction at a time. Remember, that ball was moving like that, right? But we decided to split it into two components, into this component and into that component. So those are the components that we're going to look at individually. So I'm just going to start with the x direction because I'm looking at the components individually. So I'm going to say x direction, right? Then I'm going to say, okay, in the x direction, go back up there. Let me show you something. This is V initial in the x direction of ball number 1. Initial velocity in the x direction of ball number 1. Initial velocity in the y direction of ball number 1. I'm going to look at that for my x direction, right? So I'm going to say, okay, cool. I'm going to pretend as if my ball was moving in that direction. But if I'm going to pretend that my ball was moving in that direction, then I can't say that it had this black velocity there. I have to use this velocity Vix1 because that's the component of that ball in that direction, right? So that's V initial in the x direction of ball number 1. Okay, now this is ball number 1. Now ball number 2 initially did not have a velocity, so Vix for ball number 2 was equal to 0. What was the situation after? Well, the situation after was that ball number 1 moved. So here's ball number 1 afterwards. Ball number 1 collided with ball number 2 and it moved vertically downwards, right? But since it moved vertically downwards, it means that Vix of ball number 1 was equal to, sorry, not Vix, Vfx, the final velocity of ball number 1. Final velocity of ball number 1 in the x direction is now equal to 0. It's equal to 0. Why is it equal to 0? Let me explain this a bit more. Why is it equal to 0? Let's go back up there. Notice that here's your ball number 1. It struck ball number 2 at an angle. After striking ball number 2 at an angle, look at what it did. It moved downwards vertically. So it doesn't move to the left or to the right. It moves exactly vertically downwards. Okay, since it moves downwards, it does not move this way or that way. So its velocity to the left or to the right, is 0. So it does not have a velocity to the left or to the right. So therefore, after striking ball number 2, in the x direction, the ball is still moving vertically, but in the x direction, ball number 1 stands still. Ball number 1 stands still, and ball number 2 then moves away. Ball number 2 moves away with a final velocity in the x direction that we do not know. Okay. It moves away in the x direction with the final velocity that we do not know. This is ball number 2. Okay, so now you see what we've done. We've taken a two-dimensional situation and we've converted it into a one-dimensional situation. We have a ball moving in the x direction with a certain velocity. We have a second ball just sitting there not moving. The first ball strikes the second ball and comes to a standstill. So the velocity here is 0 and the second ball moves away to the right. This is a one-dimensional analysis of momentum, and now you can calculate your momentum in that direction and you can try to find your velocities in that direction. Okay, so remember this is just one component. This is the x direction. This is the x direction, right? So your equation in the x direction, you treat it as the same way you would treat it for a one-dimensional analysis of your momentum. So you've got your mass of your ball 1. Remember the law of conservation of momentum states that the total momentum in an isolated system remains conserved or constant. So you've got m1 for mass of your ball 1 times the velocity in the x direction, the initial velocity in the x direction of your ball 1, right? That's the momentum of your ball 1, plus mass of ball 2 times the initial velocity in the x direction of ball number 2 are all equal to mass number 1 times the final velocity in the x direction of ball number 1 plus m2 mass number 2 times the final velocity in the x direction of ball number 2. Okay, and then now you can substitute and solve. I haven't actually given numbers here because I'm explaining the principle, but then now you can solve. You can see that this will fall off. What will fall off? That will fall off. It'll fall off completely because that is 0. Why is this 0? Because the initial velocity of ball number 2 was 0. The initial velocity of ball number 2 was 0, so that falls off. And this falls off here. So because the final velocity in the x direction of ball number 1 was 0. The final velocity this in the x direction was 0. So what you have now, if you simplify this further, it becomes a lot simpler. You've got m1 vi x1 is equal to m2 vf x2. Okay, and now your equation has become a lot more simple, right, to solve or to work with. Okay, but remember, this is only the beginning. This is only the beginning. You've got the other direction to look at as well. This was just looking at the x direction. We've got to look at the y direction as well. So let's look at the y direction and do a very similar analysis. Okay, so let's look at the y direction. Remember, we're dealing with momentum in two directions, two-dimensional analysis of momentum. So y direction. Okay, in the y direction, let's revisit our situation again. You have that ball, it's moving at an angle, it strikes a ball that is standing still, and then it causes this ball to move in that direction, and this ball number 1 continues to move down like that. Okay, so ball number 2 moves like that. Okay, so that's our situation. This is ball number 2, right? Ball number 2's velocity initially was 0. Ball number 1 had some velocity which we do not know, and it's in the direction that we are not wanting to look at. We want to look at two directions, the x and the y. We want to look at that direction and that direction. So we take this black direction, we find its component in the vertical direction, in the y direction, because we want to look at the y direction right now, right? We want to look at the y direction. So we take its component in the y direction, and we look at this second ball here. We also want to look at its vertical direction, right? But when you look at these two situations, what do you notice? Well, you will notice that the first ball has that vertical direction there, which is that direction there, right? So it's not that direction, it's a separate direction because this is after the collision. Okay, so it has a final velocity. So let's do this. It has ball number 1, which is that, has a final velocity in the y direction. That's the final velocity of ball number 1 in the y direction. But here we've got an initial velocity. Okay, we've got an initial velocity which we calculated from the black velocity here, from this velocity here. Okay, so here, this one, we will call it the initial velocity vi y of ball 1. Initial velocity in the y direction of ball number 1. That is that velocity before the collision. And then this velocity down here is the final velocity in the y direction for ball number 1, because it continues moving down in the vertical direction, right? We are not interested in this, in the x direction. We're really not interested in the x direction, and we're not interested in the x direction here as well, because we're looking at the vertical direction. Now, what happened to ball number 2? Ball number 2, after collision, moves to the right, but it does not have a vertical component. It moves perfectly horizontally. So it moves to the right perfectly horizontally. It does not have a vertical component. Since it doesn't have a vertical component, then it means that its vertical velocity is 0. Its velocity in the vertical direction is 0. Okay, so we know that the final velocity in the vertical direction of ball number 2 is 0. That there is 0. Okay, so what have we done now? We've essentially split this into into its own situation now, into its own scenario. We've got, if I had to redraw it, we've got that black ball moving in. Let me draw it here. We've got that black ball moving downwards here with an initial velocity in the vertical direction. This is ball number 1, right? Remember, initially it's not really moving vertically, ball number 1. Ball number 1 is moving at an angle, but we are pretending as if it's moving vertically because we're only concerned with our momentum in the vertical or in the horizontal direction or in the y and the x direction, right? So we're saying, okay, if we had to take that velocity and split it into its vertical component, which is that one there, then what are we essentially doing? What we're essentially doing is that we are saying, let's pretend as if that ball is moving vertically, because in fact it is moving a bit vertically with that velocity. If we're going to say we're pretending that it's moving vertically, then we have to give it its vertical velocity. We can't say it's moving vertically and then give it its original velocity. We've got to take the vertical component of the velocity and then we can pretend as if it's moving vertically. Okay, and remember with the other ball number 2, ball number 2 was just standing there and it's not moving. So initially, ball number 2 is not moving, right? Initially, the initial velocity in the y direction of ball number 2 is equal to 0 because the ball is not moving. Ball number 2 is not moving at all, right? Now, what happens to these balls after they collide? After these balls collide, well, this one, ball number 1, continues moving downwards. So it collided with ball number 2 such that it continues moving downwards. How do I know that it continues moving downwards? It's from the situation here, from the scenario here that we've been given. Here's the ball number 1. It's moving at an angle, and then after collision, it moves downwards, right, at that velocity, Vfy1. So that's going to be, it's moving downwards at final velocity in the y direction of ball number 1. It's moving downwards. What about ball number 2? Well, ball number 2 is moving to the right. After it got struck by ball number 1, it moved to the right. Right? It moved to the right. So now, since this ball number 2 is moving to the right, it has no vertical direction. It has no vertical direction. It's moving to the right. It has no vertical direction. So then, we're not interested in that velocity. We are interested in that velocity of the ball, but it doesn't have that velocity. Since it doesn't have that velocity, well, we are saying that ball number 1 struck ball number 2, but ball number 2 wasn't influenced by ball number 1, so it didn't move in the vertical direction. So in the vertical direction, we've got velocity, final velocity in the vertical direction, in the y direction for ball number 2 is still equal to 0. Okay, it's still equal to 0. And therefore, this is what we have. What we have is, now we've got our momentum, our momentum being conserved in the y direction. So we've got mass of ball number 1 times the initial velocity in the y direction of ball number 1 plus mass of ball 2 times the initial velocity in the y direction of ball number 2 is equal to mass of ball 1 times the final velocity of ball number 1 in the y direction plus the mass of ball number 2 times the final velocity of ball number 2 in the y direction. Okay, so I'm basically just using the law of conservation of momentum in the y direction. This is the same analysis that we did for one-dimensional momentum. Okay, and we know that initially ball number 2 did not have a velocity. Initially, ball number 2 did not have a velocity. It was just standing there, just chilling there in the y direction. It didn't have a velocity. And we also know that it still doesn't have a velocity in the y direction after the collision. So essentially, that is 0 and that is 0. pay attention. What I'm saying is ball number 2 does not have a velocity in the y direction. Ball number 2 does have a velocity in the x direction, but that's not the x direction that we're looking at, and we catered for that. We took account of that in this situation here, where m2 vfx2 is actually there and it factors into the equation, right? So ball number 2 does actually move horizontally, it doesn't move vertically, and that's why it's 0 here. Okay, so then what we have here is m1 vi y1 is equal to m1 vf y1. Okay, and then you can actually solve, and you can actually see something very interesting when you actually solve this. Okay, so now that is how you would approach this momentum in 2 dimensions. Now, something else, something important that I have to mention. Remember, in order for us to find the components of velocities, in order for us to find the components of the velocities, if we have a velocity, say we had a velocity like that, right? We have a velocity v, right? And in that direction, we've got that velocity. To find the components, we had to find vy and vx. This is vx, this is vy. Right, how do we find vx and how do we find vy? Well, we need that angle there. Okay, we need that angle there. This is theta. I'll try to write it a bit neatly. That's theta there. That angle is theta there. So vx then, from trigonometry, vx is equal to v times cos theta. This is from trigonometry. And vy is equal to v times sine theta. Okay. Vx is v times cos theta and vy is v times sine theta. And in order to find that direction, this direction here, say this direction was not given to us, in order for us to find that direction, then what we would have to say is 10. It's trigonometry. Remember, trigonometry, 10 is equal to, if you go up there, it's going to be equal to that and that, the ratio of that and that. So that's going to be opposite over adjacent, which is going to be vy over vx. Okay, so tan theta is equal to that, and this will help you find the direction. It's basically trigonometry. Okay, we will do an example demonstrating this, but you should know how to come up with these equations from trigonometry. I will make a separate video where I show through an example how to use these things and when to use them and why to use them. Okay, so I thought it's quite important for me to mention that here in this video before we actually get into examples. Okay, but just remember, because we had to find the components of the velocities, this is how you would find them. Okay, this is how you would find them. Okay, so yeah, this is essentially the momentum in 2 dimensions. It simply means that you've got 2 directions. 2 dimensions simply means that you've got 2 directions. The directions are the x and the y directions, and you've got to resolve your velocities in those directions, find your momentums in those directions, find your velocities in those directions, and then you will solve your problem easily. You can treat your problem as a one-dimensional analysis of your momentum and then solve. Okay, so that is how you would approach this. And what if they asked you to find v? What if you don't have vx and vy? Sorry, what if you have vx and vy and you don't have v and they ask you to find v? Well, another formula that is useful for you to remember from trigonometry as well, from Pythagoras, is that vx squared plus vy squared. I will show you this in an example as well. In order to avoid making this video too long, I will show you in an example. Basically, you can move from your components to your resultant, and you can move from your resultant to your components, okay, using trigonometry. Trigonometry. This is trigonometry. I will prepare a separate video relating these things to trigonometry to show how you come up with them. Okay, so that's momentum in 2 dimensions. Till next time. Lesson number one, lesson number one. Lesson number one, lesson number one.